In this video, we are going to talk about some cool projects which are using FLEX PCBs. And I really hope this video will give you some ideas how FLEX PCB could help you when you will be designing your own boards. So, what you will see? You will see a FLEX PCB robot, and we will talk about how a PCB motor can be designed. We will talk about a FLEX PCB heating vest and designing heating elements on PCBs. You will also see a ping-pong ball with over 200 LEDs. Then we will talk about a board which can solder itself, and we will talk about reliability and limitations when using FLEX PCBs in this moving display. All these projects were designed by Carl, and I had a call with Carl, which I recorded, and that's what you will see in this video. We are going to start with a FLEX PCB robot, so here it is. Here is my call with Carl. We are going to start with this, your new project, which looks really cool. And it's, what is it?
It's a folding PCB robot.
Nice. So is this like a rigid FLEX PCB, or you mentioned these are stiffeners, or how does it work?
So basically, this robot, which I call the simple bot, is made from one PCB. This is the whole PCB. And then you have these green regions that fold up. And you can see it folds up into a cube shape, sort of. And then here I'm using PCB stators to drive the wheels. Hopefully it will work.
So you created your own motor?
Yeah, so this is using the PCB motor I have been working on for the last couple of years. And
what does it mean, PCB motor? Can you?
So as you can see here, I have 6 different coils that are connected in a 3-phase system, which are then being controlled by the driving electronics over here.
So basically with these coils, you will be creating a magnetic field which is going to rotate, and the wheel has magnets, or? So
these coils generate a weak magnetic field, but that weak magnetic field is strong enough to rotate the magnets inside the rotors that are integrated into these wheels. So these wheels have 8 arc magnets, which are obviously affected by the coil's magnetic field.
Okay, and I see you design these coils. They are like triangles. Is it going to affect the magnetic field, or you did it because you wanted to fit there these 6 different coils?
This shape is basically using the most efficient area possible. So as you can see, the pitch here is only 0.1 millimeter, so it's super narrow, and this shape utilizes the area in the most efficient way possible. And is it going to be like strong enough to, move the wheels? Yeah, so a few months ago, I have been working on a 2-wheeled PCB motor that uses these same motors.
Can you show? I think you created a video. Can you show some pictures from this project? Because
yes, just give me a second.
This will also explain a little bit how the wheels actually are built.
Yeah, sure. So this is the final robot design. It started off something like this. So this was, I think, no, this was version 2 actually. So version 2, what I mean was I improved the mechanical stuff behind the wheels, because one of the main issues that I was facing was the wobble, since initially I was using a one bearing system. So here, as you can see, this is the motor that I've used in this version 1 PCB Robot. I mean, all the results that I achieved are on my YouTube channel. But this project was quite a learning journey. Initially, I had zero hopes for it to actually work.
So you just come up with the idea and you...
Yeah, from when I started the channel, I always wanted to explore the idea of building a robot made out of PCBs. So this was the first ever robot that I built from just using PCBs. So as you can see, this has these coils as well and some magnets. And what this does is basically crawl around the table. But then obviously I started as my robots, as I started exploring more robots, I started looking into the idea of making something that is actually durable. And I think with this version, I managed to achieve that, because I mean, it still has its limitations because the wheels are still low torque. And I mean, as I've showed in the videos, it cannot climb up hills yet. But I mean, when you consider other similar robots that are just made from PCBs, I think it has quite a potential.
Can you
for
make the
applications.
field stronger, like adding more?
I did manage to make to improve the magnetic field with quite an amount by using a 12-layer PCB coil that has thicker copper.
So you like created
So basically,
same coils on 12 layers, or it's one coil, or how does it work? Maybe.
sure. So this is my 12-layer coil. So what I did here is basically, so as I said, I increased the copper thickness to 2 ounce. So what the main limitations of PCB coils is the resistance. So by having a narrow track, you are basically creating a resistance, which also affects the temperature of the coil. So what I've done here is increase the copper thickness, which reduce the resistance, but at the same time add more turns, which allowed me to add more turns, but at the same time reach the same level of resistance. So that made it more efficient. Obviously, it's the main limitation here is that, for example, you cannot add this to flexible PCBs and stuff like that. And I also had to increase the pitch of the coil, because as you increase the copper thickness, you would have to also increase the clearance between the tracks. But I mean, this is the most efficient PCB coil I have ever created.
So I have a couple of questions. So you couldn't use FLEX PCB because there is limitation what can be the maximum thickness on maximum copper thickness on FLEX PCB?
The copper thickness and also the layer count, because obviously as you add more layers, the PCB will become thicker, and you would, I mean, it would no longer be considered as a flexible PCB.
I understand. So and why you had to use 12-layer PCB for this? So what is on the other layers?
So the layer count was basically calculated based on the DC resistance. So as I said, there is a relationship between the DC resistance and the temperature. So as you probably know, PCBs have a maximum temperature that can operate at, which for example, for this board has a TG value of 170 degrees Celsius. So the maximum temperature that it can operate in is around 130, 140 degrees. So basically what you need to be careful when designing PCB coils is achieve a resistance that is, I mean, first find the select a voltage level that you want to operate in, then select then from that you can get a resistance value, which you have to be careful not, like I said, not to exceed the temperature. So for example, this board can operate around 4 to 5 volts, which can achieve that maximum I said, 130, 140 degrees.
What is the current flowing through this coil?
This coil has a DC resistance of around 9 ohms. So if I remember correctly, it's around 300, 400 amps, this one. Then for the two-layer stuff, two-layer flexible PCBs, the temperature limitations are a little bit different, because flexible PCBs, from what I have found from my testing, their temperature limitation is around 100 degrees Celsius.
We will talk about this a little bit later. So
yeah, okay.
I still don't understand why it is 12 layers. So there are 12 parallel coils.
The 12 layer comes from the DC resistance. So what I
but
basically
on all the 12 layers there is same coil.
Let's open the design.
Okay.
So
because I don't understand why it needs to be, or how it helps if it's like 12 layers.
The 12 layers comes. So basically, I found a length for the copper that that needs to get the resistance that I want for the PCB not to overheat. Then I will try to fit that length in as many turns as possible.
So it is one coil on 12 layers?
It is one coil, yes.
Okay, I understand now.
Okay, let's open the PCB.
How did you know how to design this coil so fields will not cancel?
What you need to be careful of is that, let me show on the coil.
Did you also try to simulate this somehow?
What I usually do is simulate the DC resistance, because for the magnetic there are magnetic simulations, but to create a perfect model it's quite hard to do that, I think. So what I usually do is, based on my experience creating other PCB coils, so basically not by trial and error, but from experience, I basically know what kind of resistance the coil needs to be in order not to heat up. And then what I usually do is simulate an estimate value for the DC resistance.
Okay, so what is
which basically tells me how much turns I could fit as well in the coil. For your question regarding the current flow,
okay.
The current flow. So this is the connector over here. It goes around and then it enters these vias over here, which then goes to the next layer, which is this one. And as you can see, you need to be careful that the current flow still continues the same direction, and then it goes over here and continues to the other via.
And this has much stronger magnetic field, or it is much stronger magnet, basically.
Yeah, this was the most efficient PCB coil I have created, and I think unless the PCB manufacturing technology improves, this is going to be the best coil I will ever create. This PCB I'm also selling on my website as well as a kit. So anyone that would like to try out using
How
PCB
it can be
coils.
used?
I have a video on this. So basically, you can, since it's just a coil, you can use this for many applications. You can use this as an actuator, which was my main goal when I designed this. You can also use this, for example, as an electromagnet, as a weak electromagnet. From my collaboration with another YouTube channel, I managed to also attract ferrofluid with this and to control ferrofluid, which was a very interesting application. I also you can also use this as a small buzzer or perhaps even a speaker.
So does it make sound when you run current?
Yeah. So when there's a magnet nearby, if you apply a specific range of frequency, it will create sound, because it depends on whether the magnet is fixed or moving. That affects the behavior a lot. But I have also created some amounts for this, so that anyone who would like to experiment with this, he can just 3D print them out and try it out themselves. Everything is open source, so
so people can even download these files?
Yes.
Oh, that's cool. Can we go back to your robot?
Sure.
Okay. So what else is on this board?
Give me a second.
Oh, I think we wanted to see also, do you have a picture with the wheel, how the wheel is built with the magnets?
I think so, yes. So this is not the final version, but it was another version that I've tested, and it's like on the bottom. This is the bottom side of the motor. So
where did you get this kind of magnets?
So I started with using ordinary off-the-shelf magnets, but then, I mean, to continue improving this motor, I ordered these custom-made from AliExpress, and I mean there was quite significant improvement because I started by using 4 magnetic poles, and now I have 8 magnetic poles, and that was quite a huge improvement.
So did they make these magnets for you?
Yes.
There is company who can make specific magnets for you?
Yeah, if you pay, we can do anything.
How much does it cost?
I think it was around 100, 200 euros, something like that. So it was quite huge. And what usually you would usually need to buy like 100 pieces, because on AliExpress they don't, like, maybe they would give you a sample, but it's for them usually just for example ordering 10 would be more expensive than ordering 100. So
I understand. What do you have to specify? So you specify the shape, and then you specify how strong the magnets can be, or?
So basically what I did here is give them a little drawing. I will show it.
But you know, they fit perfectly, so you had to be like, I really hope they will make it exactly as I specified, because
I mean, You need to I mean, you need to specify some clearance and stuff like that as well. Because usually you have to see what is their tolerance and give a little. So this is the drawing for the magnet.
Wow. Pull force. So you specified pull force.
Yeah, that I specified that, but usually it will depend on the volume of the magnet and its area.
So it's basically
Uh,
like the strong, you ask them to make them as strong as possible.
So basically this was my wish, but if I remember correctly, I'm not sure if it was, I forgot what the value was, but it's not going to be exactly like, that's why there's a question mark there.
Wow. And then
But
you,
my important was this temperature rating was these magnets will also get a little bit hot when being used. So
because
it's
otherwise they could lose the.
yeah, they will lose their magnetic strength.
That's interesting. And how did you make the other pieces of the wheel? You have a CNC machine or something?
So this one, first I started using an aluminum rotor, which I have a small CNC machine, which I made myself. And then I started experimenting with using an iron rotor, which improved a bit the efficiency and the torque of the motor, because it helps sort of concentrate the force like on the bottom sides of the magnets. And then I switched to a combination of iron and aluminum. So I have a small plate and an aluminum housing.
Wow. Interesting. Because I would like to point out this is like many times this mechanical stuff is also a lot of thinking and a lot of work. And
Yeah. I'm a bit lucky because I also enjoy making 3D prints and stuff like that. So um, when I was back at university, I had a project that involved a lot of PCB design stuff and a lot of mechanical design stuff. So which
you
had to be
learn
3D
everything.
printed. So you had to learn mechanical design as well. I mean, I'm
So
not I probably I don't get into the stuff related to stresses and stuff like that, but for basic things like this, it's quite it does the job.
so basically you learn a lot of practical skills also at
Yeah.
university.
Yeah, I mean, when I was at university, they used to teach us both theoretical stuff and practical stuff. I mean, I think I was quite lucky to go to Malta's university because I had really great tutors here, which helped me a lot. Um, doing these practical stuff. And then in my final year, I proposed a project, which was quite complex, but I think that helped me quite a lot with both trying to design a full embedded system and also with the mechanical, how to combine like PCB and mechanical and like make them work together in a nice way.
What did you do? What kind of project?
Yeah, that's a long story. I think it's
Okay.
for another video. But my project, I'm not sure if I have any photos here. Um, my project involved designing a four-legged robot that also had coaxial propellers. Let me see if I have a photo. Because it's
How do you come up with these ideas? So you build based on your previous project, or because sometimes people they ask me like, okay, I would like to improve my skills in electronics, but I have no idea what kind of projects I should build. So how do you come up with these ideas for new projects?
Okay, some of them are, like you said, improvements based on other projects. So, for example, when I started, I just had um, I thought just building a PCB motor would be cool. But then obviously one idea leads to the next, and I mean, you cannot start from just building this robot, for example. Obviously I had to improve the efficiency of this motor to come up with something like this. And some other ideas are just ideas that are stuck in my head for like a month, and then once I have a clear path of how to make it happen, I usually start designing it.
So did you find the picture of your project, or I interrupted you?
Give me some more time because I cannot find it.
This is very good point, because it means if people are not sure or if they would like to improve skills, maybe it's good to start from smaller projects and then maybe continue.
Yeah, I mean, when I started, I started when I was a kid. I always liked to break my toys and take them apart. But then obviously going to university helped me a lot because I designed my first PCB at university. So I think that helped me introduce me to how to design circuits properly and how to also design PCBs. I think then once you have a clear basic understanding of both circuit design, I think you need to also have some understanding of software, because obviously projects like these involves a lot of software. I think then you will start tackling more difficult projects that will help you help you get more experienced and solve more interesting problems. I mean, you learn with creating problems, I think, with electronics. So this was my project.
Okay, what is it?
As you can see, this project was that project that started my hate for wires. So it had a lot of wires and stuff like this.
So that's why you do so many FLEX PCBs?
I think this because I mean when I was during this time I used to fantasize about selling this, because during the time drones were like starting out and
It
stuff
was
like
before
that.
the
Yeah,
DJ.
the drone explosion. But you obviously cannot sell stuff like this with all those wires, and maybe like a kit, but it's still a headache to get manufactured. So flexible PCBs, I think, is makes everything neatly and.
So this is like a spider or something?
So yes, this has four legs with 3 degrees of freedom each leg. So it has 3 joints and 3 servos per each leg. And then here I have like two propellers that are coaxial. So the idea for this robot was to make it walk and fly at the same time. I didn't actually reach that point because I mean it had to go through some other iterations before actually try and make that happen. because for this robot I decided to do everything custom made. So for example, the controllers for the brushless motors, I designed the PCB and written the software myself. And obviously, since there are so many motors and so many stuff to control, I didn't manage to complete everything in time. So for example, I mean, it managed to do some kinematic moves and stuff like that to dance around, but I didn't manage to actually control it during flight.
I keep thinking like I only see one
Propeller.
yeah. So how do you control
It's
balance of this?
there's another propeller at the bottom over
Oh,
here.
and they are
I don't.
spinning like different directions.
Yeah, yeah.
Or...
So that will basically stabilize the.
Yeah, so it's not rotating.
Yeah, yeah.
And then how do you control left and right balance?
The idea, the novel idea behind this was to control the balance using the weight of the batteries. So that was I think another thesis on its own.
So you could move the legs, for example. So
the legs, yes.
So you balance the center of gravity or something.
So basically, the heaviest part of this robot was the tip of the legs. So you can see that there are the batteries, 4 batteries in each leg.
So it's like a rocket or something. Like if you put the center of gravity in the right position, it will always face
yes,
up.
yes. So basically, move the center of gravity of the robot. I mean, this was just theoretical, but I would love to someday perhaps revisit this project. The main limitation was for this project was the battery life, because obviously you need to have the robot needs to walk and fly at the same time. So what I estimated is that during flight mode it will just be used for just like 2 minutes, for example, because the weight of the batteries versus their capacity wasn't that good.
Wow. Cool. Let's go back to your.
But I mean, this project, I think I learned a lot of lessons from this project, because first it had the weight limitation, which from a design point of view,
virus. You learned virus.
Yeah.
So what did you learn about virus? They are unreliable, or they are heavy, or
not
it's a lot of work?
I mean, my main lesson was that, I mean, if you're going to build something just for fun, they are okay. But if you're going to have perhaps design something that can actually be used for a real life application, it's going to be for robots, obviously. I'm just talking about robots because there are other use cases that, I mean, wires will do the job just fine. But with robots, you have to design something that is easy to build and, I think, repair free as well.
It's not only about robots. I've seen cables are often like difficult because you need extra people or work to, you know, build it or assemble the cables, and they are not always reliable. Like they can move, then they lose connection or something. And okay, let's go back to your project, your current project. Okay, so what do we have on this board? So there are the coils. Okay.
To the view, I think it would be easier to explain. Okay. Okay, so here, as you can see, there is an ESP32. This is
so the ESP. That's the one with wireless or Bluetooth, or what is it?
So it have both, I believe.
Wi-Fi and Bluetooth.
Yeah. And then here there is an IMU. The idea behind this was so that if the wheels would have So if the robot would like, when it moves, it would have a clear idea of its orientation, and it could also compensate for any tilting that the wheels introduce. Then I have these 4 LEDs that are back mounted
So they are visible from out.
from the back side.
So
Here
are
I
these
have,
like special components?
no, you can actually,
You just swap them upside down and solder them upside down?
yeah, they are meant to be soldered upside down.
Okay.
And they also specify you the exact hole diameter for them to be mounted correctly and stuff like that. Here I have just an optical sensor, perhaps a proximity sensor, so that I could detect walls and stuff like that. Then over here I have the 4 controllers for the motors. I also
For the
have
coils,
yeah. I also have a battery charger. I think that's it, and the regulator here. That's it.
So there are
main,
the controllers, they are just switching the coils, or what are the other 4 chips? These are like PVM chips or something?
So the main disadvantage of using brushless or 3-phase motors is that you need to have a microcontroller to control the motor. So each motor here I have its own microcontroller and its own 3-phase driver.
Okay, that's what I thought. Okay, perfect. So when it is going to?
Hopefully by next month, if I don't run into any specific problems.
I'm really curious to see video on this. But it should work because you build the 2-wheel robot.
Yeah, I mean, in theory, it should work. I already soldered the PCB. I'm just testing out that everything is working correctly and writing the software for all the microcontrollers. And
did you mention this stiffener is aluminum or something?
Yeah, so these stiffeners at the top side are FR4 stiffeners, and on the back side, I am using steel stiffeners. So
can they do that? Who is manufacturing this PCB way or?
PCB way, yes.
So they can.
Yes, you can specify
steel stiffener.
And what kind of stiffener would you like to introduce at the back and at the top? They can be different.
Wow.
I think last week they also introduced aluminum stiffeners, which I think will be better. The main disadvantage of using steel or aluminum is that when you solder them, you run into the issue that it will take longer to solder them because the metal will absorb some of the heat.
But aluminum can be lighter a little bit now comparing to steel.
Yes.
Okay, and how did you specify how to manufacture this? Because it's quite complex PCB. So how you specify all the layers?
Sure. What I do is, so this is the outline. So the easiest way I found to, because as you can see, this has a lot of stiffeners and areas and stuff like this. What I do is usually create a separate mechanical layer for both the top stiffeners and bottom stiffeners, and specify the area that I would like the stiffener to be used in. So this, for example, I also usually like to label these so that they will know how many stiffeners there are.
And they can build it based on this mechanical layer. They can create the shape and place it exactly on the
Exactly.
Okay. So you don't really need to use the special stack-up flex features which Altium has.
I mean, what I usually do is use that just to create animations like this, but because it just looks really cool for the video. But to design it's usually I find it quicker to just add another mechanical layer and design that.
This is good to know, because even people who are using KiCad, for example, they can now they will know they don't really need any fancy flex features. They can just use another layer and easy manufacture flex PCBs. Exactly as you mentioned, when I was doing my flex PCB, I used this Altium's feature just to show how it is going to look, because when you specify all these different layers, then in 3D view you can actually see kind of your PCB is more realistic, because the stiffener has different color comparing to flex PCB itself, and then you can visualize it better.
Yeah, what I did here, and then I added like a 3D body, which also allows you to get, so I use this feature, which also allows you to make the PCB look more realistic.
So it folds together with, yeah, of course it folds together with the 3D body.
So for
that's
example,
cool tip.
Here you can also change the color if you like of the stiffeners and stuff like that, of the 3D body that I created there. Give me a second. Okay, I think it's for the other side. Let me check. Give me a second. Okay, there it is. I saw it. Sorry for the lag, because I think the camera. So you can just make it more realistic that way, I think.
It looks really good. And Flex, PCB Way, they sponsor your PCBs.
Yeah, yeah.
So you don't have to pay for all the experiments you do.
That's the benefit of doing YouTube and stuff like that.
They are cool. Yeah, they have sent me a number of emails, and I've been working actually with PCB Way some time ago. But I don't want to make advertisement for them. But it can be really helpful if PC manufacturer can support these kind of projects. Otherwise, it would cost a lot of money, because I think you build like huge flex PCB when you created your Vest.
So I recently created.
So this is different project.
This Vest. Let me find it. Sorry. Give me a second.
Yeah, so not this one. This one, yeah. So you would, if you would not be sponsored, you would not be buying this one.
I don't think so. So this is a huge, the biggest PCB I have ever created, which is last year I made a lot of experiments related to thermal flexible PCBs. And the idea was to create like a wearable vest using. I mean, there were a lot of my viewers who pointed out that you cannot wear it in like this in like an airport and stuff like that, and they are right. But it was fun making this project, I think.
How big is it?
Let me.
It's like half meter.
It's around 70 centimeters, I think. Yeah, it's 70.
It's almost 1 meter. Like.
Yeah. Before I start designing it, I asked my PCB manufacturer what's the maximum size they can.
So what is the maximum size?
It's around 1.2 meters for flexible PCBs.
Wow.
So I could have gone a little bit larger.
So how does this work? Is it really working? Is it?
Yeah, it does work. The main limitation of it are the batteries. So I place the batteries on the back side, and they are kind of bulky. So that's the main. But I mean, it was just for fun. So this works. So it basically has a temperature controller over here, and then it has this thermal track that heats up. It's like a resistor that heats up. That goes all the way to the back.
Again, you had to calculate the
Yes.
width or and length.
The resistance mainly. So I from the resistance I got the width and length of the track.
How did you know what kind of resistance you can expect for specific track geometry?
Okay, so when I started, when I created my first PCB heater, because I have created multiple heaters on my channel, I actually got the resistance wrong because I based it based on the resistance on a small flexible PCB, and when you make things larger, and also the first PCB was an FR4 PCB, an aluminum PCB, sorry. The term it's required its resistance was higher, so it required a much larger voltage for it to heat up for the temperatures I wanted. But then I made some research and found that the printers have a heat bed, which is usually a PCB, and I found that that's usually less than 10 ohms, so I based it on that. And I mean, I managed to get accurate results based on that.
So did you create your own calculator, or?
So basically, I selected the resistance, so my goal resistance sort of, which was like 1 or 2 ohms. And then what I usually do, specify, play around a little with either the length or the width of the track. So,
but still, you need some kind of calculator to know.
Yeah, what I usually use is Saturn PCB tool, which is free.
Oh, so it's so accurate. It can give you accurate numbers.
I think it's never going to be that accurate, but it gives you quite a good estimate that will work.
Cool. Okay, so what is the current and what is the voltage to drive this?
To drive this, I forgot a little. To drive this, I'm using a 3-cell LiPo battery, I believe. And the current was around, I'm not sure, I forgot. I think it was around 1.5 amps, something like that. It depends also. It depends also on the
voltage.
On the temperature.
Okay, on the temperature.
We would like for it to heat up. So
what is the maximum temperature you can? Are you going to burn yourself?
You can be like, but I think I limited to around 40, something like 40, 50 degrees.
So there is a sensor somewhere?
Yes, there's a small sensor over here. There was a little temperature difference between the maximum temperature heating point and this area over here. But you can compensate it in software if you like.
How do you know? So you use thermal camera to find out what was the hottest?
Yes. Okay. Yes, I have a thermal.
What kind of thermal camera do you use?
I used to use one. I'm not sure about the brand, but I recently got the FLER thermal camera. The
real one, or for iPhone and iPad?
And for the phone.
For the phone, yeah. I have the FLER. I don't know which one it is.
I think it was a good purchase because I was doing a lot of projects related to thermal, and I wasn't filming them like that professionally. So
okay, what is the next project what you created?
So hopefully I'm going to release a new video this week related. I created a PCB actuator driver, which I'm going to sell on my website. So that
When you say actuator driver, so what is it doing?
This driver, let me go on. So this is the data sheet I made for this driver. So what my goal for this was to create a small driver that people could use to get started more easily with PCB actuators. So this allows you to either control the speed, the position, and you can also use it as a buzzer or just control it externally. So it has like 6 different modes you could use to drive the actuator.
So you use this together with the coils.
Yes. So
Okay.
you could use it for some, if you'd like me to show you some applications. These are some applications, for example, that can be used, and like here it's like back to back with the PCB coil, so that you could use it for a lot of interesting custom applications.
Okay. And then I think you created this ping-pong LED ball.
Yeah.
That's what really like when I saw your channel. I think this was like the first project I noticed.
Okay.
Because visually it's like it looks super cool.
Yeah.
Show the finished project first out so people can see it.
Okay. I think this was one of the most complex, flexible PCB projects I have created, because to get it right, it was quite a challenge.
And you did it just for fun, yeah?
Yeah.
You must have a lot of free time.
I mean, doing this YouTube project stuff is also my job, so I am quite lucky, I think. So this is the
This looks
ball.
really good.
Yeah, I managed to play ping pong with it. So this I made that a case for it. It has 242 LEDs.
Wow.
RGB LED, addressable RGB LEDs. It was quite a challenging project because first of all I had to get it under under 44 centimeters diameter, so I had to fit everything in just a small ball, like a ping pong size ball. And obviously I had to fit all the electronics, the battery, make sure that the LEDs will fold into a sphere. So it took me a little to get the right shape for it to fold into an actual ball.
I would like to ask before we continue, how do you do, or how far you go with software? Because we haven't speak about software, and I know like building this hardware is quite a lot of work because I've done recently I've done the Wizard One project. I don't know if you have seen this, but
Yeah, so
yeah, okay. So once it works and you know hardware is perfectly fine, I do the basic software test, everything is working, but then make it like perfect.
yeah,
You know, that would be a lot of work on software. So
it is. So I mean, I think software usually. I'm not sure. It's different for every project, but it takes a lot of time if you want to get the software
perfect, yeah.
I don't always get too fancy on software. Sometimes, I mean, if it works, it's just going to be a YouTube video. For example, this was a project like that. But when it comes to, for example, the Flexar driver, which I showed you before this, that involved a lot of refinements in the software so that I could achieve the maximum performance from the driver.
So what kind of software you created for this ball? What does
so
it
the
do?
software for this ball I created using the Arduino IDE. What it does is basically here we have a little accelerometer. So every time it hits the pellet, it changes the color of the ball. So that was the main idea behind it.
Can you control each LED individually? No.
Yes, because they are
really
adjustable.
So these are the special LEDs with like IDs or something like that. So you can access every single LED and set color of every single LED.
Yes.
Wow. So you could even make like display from this, like for example, count number of bouncings or something.
Exactly.
That's cool. Wow. Okay, so let's continue about this.
So that I think the most challenging part, like I said, is folding the shape into a spherical object. The way I did it was testing it with 3D print. So I printed a single layer of PLA and just before I ordered the PCB, I tested multiple prototypes on how they're going to fold into a sphere.
I did exactly same when I was building my FLEX PCB. I just printed, I think, 1 or 2 layers of
you can
3D
also
print.
export the step file if you like of the PCB and just print it as it is.
Yeah, and you can test
that's
if it's
quite
going
a
to
useful.
bend correctly.
That's quite a useful feature, I think.
So I think you opened the 3D model of the ball, so we can see how it looks. Okay.
Okay, this is one. I also have the main assembly.
You use Fusion 360 for mechanical designs.
Yes.
Okay. You imported, this is the PCB imported from Altium?
Yes. So here I basically tested that the PCB fits and everything like that. I didn't test the bending stuff.
Yeah, because I was thinking you can't really test the bending.
I'm not sure. I'm sure there's a way, but I mean, it wasn't that important.
Yeah, you would have to do it probably different way, like import this ball to Altium and then do the bending in Altium.
I think so, yes. Because in Altium it's a little easier, although it's still hard to like fold this into a semi-sphere because I think it's just one bend. You cannot do multiple bends for each.
And you 3D printed this ball, correct?
Yes.
Wow. Okay, let's have a look what is on the PCB. So there is the again you use this STM everywhere.
Yeah, I didn't usually use it, but a lot of my viewers always requested it, and I think it's very open source friendly. So when
which one is it? Which one is it? specifically?
The ESP32.
But
So
it needs to have some kind of specific number, no? Because it's kind of
I think
module,
it's
or what is it?
ESP2 worm. So this is the part number.
Ah, okay, ESP. Okay. And then how do you
It's
program this? You say you use Arduino IDE.
yes. So you basically program it over UART.
UART. So you need like UART to USB cable or something.
Yes, yes.
Which one you use? The FTDI cables or?
Yeah, I mean the FTDI. I mean there's a lot of different. I have some different brands. I'm not sure what they are. What brand they are.
Okay, and there is basically, how do you drive all the LEDs? Do you need some special driver or something? Because it must drive some quite of current, no? Or how much one LED needs?
Its supply range. It's I think its maximum supply range is around 4 or 5 volts. So I think it's 4.5 to 5 volts, something like that. So to power it, so here I had a LiPo battery. The supplies of the LEDs was directly connected to the battery, and then it has a different logic level as well. So the logic level was 3.3 volts compatible, which the data was generated using the microcontroller.
Do you know how much current does it drive when you use white, full bright?
I since the LiPo battery was quite small, I had to reduce the brightness of the LEDs, which can also be done using software. So I limited it a little so that it wouldn't damage the battery or something like that.
Because even if you drive like 1 milliamp, you say there was over 100.
242.
200. So even if it's like 1 milliamp, that's 200 milliamps for 200
exactly.
LEDs.
I think it wasn't over 500 milliamps. Because like I said, I had to reduce the brightness. I'm sure if I had to, so each LED was being driven with like less than, I believe less than 20 milliamps or 10 milliamps, something like that. I think it was 10 milliamps each LED.
Oh yeah, because in each LED there are actually 3 LEDs, and if you would like to use white, you need to turn on all of them. And so how do you solder these?
For these type of flexible PCBs, the best approach I found was using a hot plate. Because like I said, flexible PCBs, their maximum temperature for a short period of time cannot exceed 200 degrees, I think. So what I usually do is use low temperature solder paste, which reflows at around 160 degrees Celsius, and then solder it on my hot plate.
Can we see some pictures? So you also always order a stiffener or stencil, sorry.
Yes, for these kind of projects, stencils always required, because some of these are like 0402 and you have fine pitches over here.
And then manually you place all the...
And the LEDs are also very small. It's like 1.5 by 1.5. So given there's 242, it would be quite a headache not to have a stencil.
Did you place some of them the different, way, and you had to...
Yeah, I think so, yes. Some of them.
So you have your own plate?
Yes, I have.
I think
I
I've
so
seen in some of your videos you build it by
I
yourself from PCB or?
I have built a PCB hot plate, but which is this one. So this is the assembly video of the ball.
Mm-hmm.
This one is using the PCB hot plate, but I don't recommend using this for, I mean, because it's not meant to exceed the temperature.
I've seen
So
it puffed a little bit when.
yeah, I have a video on that on my YouTube channel. Um,
Yeah, here it is visible. Yeah.
yeah, so it's this one.
Mm-hmm.
I have two videos, this and this, regarding temperature testing on flexible PCBs. So here I tried to basically reflow PCBs with a PCB hot plate with another PCB.
Mm-hmm.
I have another project coming up that tries a different technique, because what I found here is that it cannot be reused. Like, so for one time, it's powering it at 160 degrees Celsius for 4 minutes or something like that. It should be okay,
Mm-hmm.
but it's not reusable. So I have another project coming up that I'm going to test self-reflowing PCBs. So as you know, PCBs is made.
Self-reflowing.
Yeah,
So you just put their components, you connect power, and they will
yeah,
solder themselves.
yes. So the way I'm going to do it is the PCB is going to be 4 layers, I think. Let me open the project also.
This is
And
interesting.
then you have another layer that is like the thermal layer that could reflow the PCB. So this is the project that I talked about.
So this is going to solder itself.
Yeah. So this is going to be like this has two functions. So it can solder itself. So you just apply power on this, and the PCB will reflow. And then once you flash the software and everything, it could also act as a temperature controller to reflow another PCB. So basically, imagine having two of these PCBs. You connect the terminal in here, and it can control the reflow profile of the other PCB.
That's interesting.
So it's like creating. The first concept I had, I called this like a mother. So it's like having a mother that creates other.
It's like the
baby
very first 3D
PCBs.
printer which can 3D print
Exactly,
parts for the
exactly,
other 3D printers.
exactly, exactly. So here is the thermal track. I should release this, I think, in August or September, because the next project is going to be the robot, and then I'm going to start working on this.
Interesting. Okay, what else we have on the list? Oh, this is the display.
The display, yes.
So this was on your YouTube channel. I've seen this was one of your like very popular videos.
Yeah, this was my most popular video. So this is.
I would like to say I think it's like over 2 million views.
Yeah, it's quite. It went quite popular on YouTube. Let me flip this around. So the way this works is I've designed this a couple of years ago, so I think it was 2 years ago or 3. So it has 2 coils and a couple of RGB LEDs. And then it has an LED driver that can control the current and the color of each LED, and make sure that it's also because this one is a constant current driver. And then I have a microcontroller that controls the color of the LED so that it could display some words or some animations. The main issue with this project is durability, which I have another video planned. I'm currently testing the durability of flexible PCB. So testing, for example, the lifetime of the...
How much you can
because
bend it, yeah.
because
How
this
many times you
was...
can bend it?
It can flap because this flaps at around, I think, 25 hertz, which was the maximum speed I could achieve with this
Can we show
prototype.
pictures so people can see actually how it works?
Okay, so this is it flapping. Then I have... This is it unpowered because I also made a little mount for it.
So basically the upper part is moving, yeah. And
and I managed to create like shapes like this.
How do you know, like, you are just guessing the position of this, or how do you know in what position it is located?
Okay. So here the position was being done in open loop. So I just measured the frequency at which it was
And you
flapping.
divided it some
Exactly, and I divided it by 16.
resolution of the
The resolution. So I assume that, for example, if it's going to take 0.1 milliseconds for it to go from here to here, I just divided it into... Obviously, then you have another issue because, as you can see, not every pixel is the same size as well.
Because it's not the same
it's
speed.
not exactly.
But yeah, this is interesting. So what did you find out about how many times it can bend?
I'm still running some tests, but and the tests were not run on the specific PCB, but I ran the test on some other PCBs. They could flap around a couple of million times, but I mean a couple of million times could mean days. So I'm still running some testing on them and evaluating the results, which I will hopefully summarize into a whole video. Because I also went into analyzing the durability of the thermal aspects of the PCB and for example, for flexible PCBs, I found that the silk screen on the coils, if you at 100 degrees after a couple of, I think it was around 1-2 weeks, it will start to discolor a little. It will start turning into a yellowish color, and stuff like that.
So what will happen when it bends too many times? The copper is going to break?
Yeah, the copper will start breaking, I believe. I'm not assuming this, but I'm pretty sure it's the case because to know for sure you have to have it X-rayed, I think. But I think it's pretty sure it's the copper because if you try to like hold it with your fingers, it will start flapping again. So I'm pretty sure it's the copper from the arm that's breaking.
So, and is it going to happen also if you use like wider tracks, or?
Sorry?
If you use wider tracks, is it going to
that's one of the things that I'm testing.
Because
but if you use wider...
it still should theoretically break.
Yeah, but I think you would extend the lifetime of it. But the main because if you extend the copper, you will also limit the flapping angle of it as well. So that other than that, this prototype also had the LEDs that were a little fragile as well. So I wasn't using the LEDs were too fragile, I think, for it.
So what happened with the LEDs? They just stopped working.
Yeah. So here, for example,
because of this movement.
Yeah, they will either the soldering joints will break, or I think the LED itself will stop working.
Something inside of the LED will break.
Yeah.
Wow.
There was a time where I started experimenting with AC-curated LEDs, which can handle tougher stress-related environments. But those LEDs are usually a little bit heavy, especially the RGB ones. So, and you don't always find them in a right-angled package.
This is interesting. I would never say because of these vibrations a component can actually break.
But remember, this is going at around 25 hertz, so it's being it's quite stressful, I think, especially for the soldering joints.
Okay, so what are your recommendations for designing flex PCBs? What is different from designing rigid PCBs comparing to flex PCBs? I know, for example, when you are designing the part of the flex which is going to bend, and there is I don't know, right angle, then you should maybe use like rounded corner or something like this.
Exactly. There are some guidelines that can help you, for example, for the bending radius and stuff like that, how to calculate the radius and not to make sharp corners. For example, you can also hedge the copper planes to make it more flexible. There are some tips like these you can find on the internet. But I think with flex PCBs, you start gaining experience just from doing it. That's how I learned. I mean, I never before making YouTube videos, I have never designed a flexible PCB. So I mean, if you go through all my YouTube channel, you could see me sort of learn
all the kind of improvements what you had to do.
See the mistakes I made.
I didn't want to say it that way. You did it.
Yeah, but it's okay to say it because I mean, part of engineering is failure.
That's why I
think it's the most important part of engineering.
Yeah, that's why I wanted to talk about this little bit. So is there something like what you really think people should be careful about when designing flex PCBs? What is like most difference? Like, be careful about this because
I think from a practical point of view, it's the same. I mean, you can just design a normal PCB and specify that it would be flex. The same. The only thing that's different is the mechanical aspect. So, for example, this project over here, how it's going to bend, is the angle going to be correct, and stuff like that. For example, the length of this. The length of this piece of plastic over here, how long does it going to be? And I mean, you can calculate that using basic maths, I think. So it's not that hard. It's just, I think, more. It takes a little bit more time and more. It involves more mechanical thinking, sort of.
So basically, if the flex would be flat, then it could be exactly same as rigid PCB.
And then what you have to be careful is that you place, for example, underneath components, if the component is going to be flexed, you have to place stiffeners and stuff like that. So not everything can bend, because you will actually break the soldering joints of chips.
This is
and
what I
stuff.
was thinking about when I've seen your when I've seen the FLEX PCB for the ball. Like you soldered all the LEDs and then you bended it. So I was
Yeah,
thinking like, is this going to like damage the parts or?
yeah. I mean, I haven't tested it for like to to manufacture it or something like that. That project was just for fun. But from my experience, if it's like a one-time bend, it should be okay.
Mm-hmm.
If you're going to, for example, if it's going to be like a laptop or something, have a hinge that opens
Mm-hmm.
multiple times, you need to be careful there,
Mm-hmm.
because the component, you have a soldering joint or something like that there, it can easily break.
Mm-hmm. On the Instagram, there were 3 questions.
Okay.
One was about your career path.
Okay.
So what can you tell us? I know
Okay.
you studied at university. You already mentioned this.
Okay. So after graduating from electronics engineering, the first thing that I did is start a startup with my friend.
You even didn't
So
go to, work for a company. You
I,
directly went
I,
for
I
startup.
yeah, because I live in Malta, so there's not a lot of companies related to
Oh.
electronics. And I was really passionate about like product design and stuff like that. So I really wanted to just design PCBs and sell them. So, but that obviously requires a lot of money. So we had to stop after around 8, 9 months. Um,
And what did you design?
we were working on 2 different projects, a small drone and a Bluetooth alarm tag.
Mm-hmm.
So those were the 2 different projects that we heavily worked on. But like I said, we had to stop.
So it was like only about money, or what
I
did you feel like?
I
Mm,
think, I mean, we spent 9 months not earning any money. We just
okay.
designed stuff and test stuff. So we couldn't do it any longer. And so then I managed to find a job working in an automotive industry. Um, so I worked in a company that sells parts and designs parts for um, new cars and stuff like that. It was a very interesting job because um, I had met really interesting people that works in a lot of high-end companies. So
So it
I
was a local company in Malta.
Yeah, it's a local company in
Mm-hmm.
Malta, I think one of the best electronics design company in Malta. Um, and I first started working on developing electronic prototypes for concept vehicles. And then I switched to writing firmware um, for these automotive parts. I learned a lot from them because some of that stuff is safety critical and stuff like that.
Mm-hmm.
So that that was what I did. I obviously started YouTube and working on my projects on my free time. And then in 2020, I started this YouTube thing full time.
Mm-hmm. Cool. So this is interesting. So yeah, if someone would like to start startup directly after university, be prepared. You need a lot of money. Correct?
I mean, I mean, when starting a startup, I think you always need a
Always
lot of
need a
money.
lot of money. That's very good point.
I think looking at it right today, it's I think you cannot just start a startup because, for example, personally, I like to work on different projects
Mm-hmm.
first of all. And I mean, YouTube allows you to do that because you just work on different projects and not get stuck on a project for like years. So it's a little bit refreshing as well.
Do you
And
think
then,
you need experience? Like, did you find it useful to work in a
yeah,
company and see all the kind
yes,
of ways how they actually approach and
yes.
work? Okay.
I think you need that kind of experience as well. I found that a bit challenging because I don't like the corporate stuff. So I found it very hard to work on, for example, projects that I didn't like or stuff like that. Because I mean, you will be assigned to a project. You don't have the say on what you want to do. So from that side, being a self-employed and a YouTuber gives you a little more freedom. But I think you have to have an experience in the industry is quite it's needed as well.
This is going to be a hard question to answer. So, do you make enough money just from YouTube to be able to, do what you like to do?
Yeah, so far it's not so YouTube it's a little bit random, so it's not that stable, but so far because I don't just do YouTube, I also sell some kits on my website, and I do other stuff. For example, I do Instagram as well, and all that stuff. I managed to make an income from it.
So that was the first question. Now the second question from Instagram was if it's possible, or how to calculate the temperature in FLEX PCBs. We were talking about this.
Yeah,
So can you do it? Can you calculate it?
So I think we answered a little bit at one point. What I do is usually define that goal resistance, which is around 1 to 2 ohms, and then try to select a voltage and calculate the length of the resistance based on the width that I select.
So the resistance 1 ohm is which will give you the 100.
No, 1 ohm, what it means is that at around 5 to 12 volts, it will get you to around 100 degrees.
Yeah, that's what. Yeah, okay, that's what I mean. And if it's like lower.
And then it also depends on the area a little bit and whether it's flexible or not. But I mean, it's quite similar. So, for example, I have a PCB that has the same 1 ohm resistance, but since it's very small, it was just like at 1 volt it reached 100 degrees, and then a PCB with the same resistance but in a 10 by 10 centimeters, it reaches 100 degrees at 5 volts. It's just a question of power, I think.
Okay. And that's everything for this video. I would like to say thank you very much to Carl for helping me to create this video. Thank you, Carl. And if you have any questions, don't forget to leave them in the comments. And, give some feedback. I would like to know if you like this video. If you like it, also don't forget press the like button. And if you would like to get notified about my future videos, if you like this kind of videos, then don't forget to subscribe. It helps a lot. Thank you very much for watching and see you next time. Bye.